I have a great pleasure to host Professor Vlatko Vedral, who is well-known and brilliant physicist. Professor Vedral, thank you so much for doing this interview.
Thank you.
You once said that that the world exists only when it's not observed. What did you mean by that?
And that's an excellent question because, in quantum physics, when people talk about quantum mechanics, they usually say the opposite. Mm-hmm. They go with Bishop Berkeley, right, who said that, the famous statement that, if there is no one in the forest to hear the sound of a tree falling, mm-hmm. Did it really happen or not? And he would claim no, because he would say it's all about observation. If there wasn't an observer to perceive it, then it didn't happen. It's an extreme form of idealism. And I think it kind of at some point it hit me that quantum mechanics is actually the opposite of that, in the sense that there is much more to reality out there. But when we engage, when we make an observation, we only get a subset of the whole thing. So we can perceive one property or another property, but quantum mechanics doesn't allow us to perceive all of the properties at the same time.
Right. Would it be possible to find a theory of the world as a whole, the ultimate theory of everything?
Oh, good. That's a difficult question. I think at the moment, that's not clear at all that there will be a theory of everything of that kind. I think at the moment, we have quantum physics, and quantum physics works really well in most of the domains. We don't know if things like gravity are quantum mechanical. We haven't gone fully into the macroscopic world. Bits of chemistry are not necessarily understood fully quantum mechanically, biology definitely. So this is outstanding. But I think if you look at it in terms of the theory itself, it's consistent. It's possible to think about the whole world as quantum mechanical. There are no contradictions. But like I said, it's hard to imagine that this is the last word. I mean, somehow, as a scientist, you're always thinking, well, sooner or later, there will be some experiment that will probably contradict quantum mechanics as well, and then we have to think about it.
Right. To what extent do you agree with the phrase universe as a quantum computer?
Oh, yeah, another good question. I think it's a helpful analogy, and I think in my writing and in my book, in Decoding Reality, I was saying how, with every new epoch and how we understand the world in terms of whatever is the up-to-date scientific understanding, we usually like to project that on the whole universe. So, during Industrial Revolution, thermodynamics was the kind of theory at that time that was very much investigated. And then people immediately thought not just about steam engines, but what about the whole universe? Could the whole universe be subject to the laws of thermodynamics? Is it some kind of engine, if you like? But I think the paradigm later became really computer in terms of information processing. It seems to me that that's closer to how quantum mechanics works as well, that you should really think about basic interactions in the universe as some kind of information processing protocol, in a sense. Now, what's really missing in this, I'm hesitating to say that that's really it's more like a metaphor in a way. The reason being that we don't really know to what degree we can really program larger and larger chunks of the universe. So, if I tell you universe is a computer, you can immediately say, how do I program the universe to do ABC for me? And we don't know that. We know that with computers, we can see how that could be enlarged maybe to larger entities, more complex than computers. But whether the whole universe could ultimately be somehow programmed and controlled is a big question. So that's where you would stop maybe with this metaphor.
Right. So what do you find fascinating about quantum entanglement? And do you agree with Einstein's definition of quantum entanglement as spooky action?
Very nice. Very nice. Yes, I would not agree with the spooky action at the distance, in the sense that I think what really made him nervous at that time, and of course, he was the the discoverer of relativity as well. I think he felt that quantum mechanics was clashing with relativity. And I think, even the very concept of superposition, which leads to entanglement, was a problem for him, because he thought, let's say I even have a particle, like a photon, in two places at the same time, really quantum mechanically in a superposition. What worried him is that the extent of this superposition could be arbitrarily large, but as soon as I make a measurement to determine whether the particle is here or it's not here, I automatically understand what's going on at the distance. So he would say, look, I put a detector here, I don't get a click. Suddenly the photon appears over there across the universe. How can that be? Spooky action at the distance, right? No detection here creates a particle there. If you do this in this kind of anti-Berkeley way that I like, that actually there is more to reality. And if your elements of reality are not just numbers, but as quantum mechanics would say, are these more complex things that we call observables. I think Dirac called them quantum numbers. So they are a generalized form of a number. If you believe that those are your elements of reality, and you can, at every point you can specify these quantum numbers, then there is no spooky action at the distance. And that's a beautiful thing. Quantum mechanics, much like classical field theory, describes exactly what I now explained in a purely causal way. So basically you get a click here that propagates at the speed of light at most to the other place, and then you can change the state at the other place and so on. So in that sense, there isn't anything really that violates relativity. It can be made fully to comply with relativity. And all the experiments so far seem to suggest that. So of course, this is not to say that one day someone won't come along and show otherwise. But I think at the moment there is nothing spooky in quantum mechanics.
I see. So you often think about philosophy and metaphysics. Do you consider yourself as a realist or idealist when it comes to understanding of the world?
Very good question. So again, Berkeley would be like your prime example of an idealist, I think all scientists really are realists in the sense that there is certainly some world out there that we are experimenting on and perceiving and trying to maybe control as engineers in some way. Of course, it would be naive to think that the world out there really is exactly as we perceive it. And in fact, the whole point of science is to show us that there is much more to the world than what we see, which is exactly what forces us into conjuring up these more and more complex entities. So when I tell you that quantum numbers are the ultimate reality as far as quantum physics is concerned, it is very far removed from our perception. And like I said, quantum mechanics even says you can't perceive a quantum number in a single shot experiment. You have to do many experiments and construct it out of these many experiments. So in that sense, I would say I'm a realist, but you have to be careful when you say that, because in physics, sometimes by realist, you mean classical realist. I believe that the real numbers are there and they describe everything and that's it. If you say that, then you've got a problem with quantum mechanics, because you're effectively giving a hidden variable theory, and we know that there are no such things. However, if you acknowledge that the elements of reality are these more complex entities, then I think there's no problem with that. So I would say I'm a kind of quantum realist, if you see what I mean. That's the idea.
I understand.
Yes.
So the phrase you particularly like is being versus becoming.
Yes.
So how do you perceive time and uncertainty?
Yes, you're asking me all of these very difficult and profound questions because we don't really have an answer to that. I actually like both of these pictures, and I think depending on the problem you're thinking about, either of them may be more suitable, maybe easier to work with. So physics does have a mode in which everything is becoming. In fact, our dynamical evolution, how we describe dynamics, you could think of as the world of becoming. But there is a picture of quantum mechanics, even classical physics, which is entirely static, which says, oh, the whole universe exists in some huge quantum state. And when I say the whole universe now, I'm including space and time.
Right.
So that means all of the instances in time are actually given to you once and for all. And you can actually phrase quantum mechanics this way. There is no paradox there at all. And in fact, you yourself exist in these different times simultaneously in this huge quantum mechanical state. So it's very interesting to me that these, you call them metaphysical, and I think it could well be that these are questions ultimately beyond physics, because it seems to us that even with making huge advances in physics, we actually ultimately come back to the same questions. And you say, okay, now we understand the world is quantum. So how should I think of time? Does time flow? Or is time static and I flow through time? All of these confusing ideas. And actually, I think all of these pictures are ultimately valid and you can, in fact, do physics in all of them. You may prefer one of them, a bit like how some people prefer one interpretation of quantum mechanics over another. But I don't think we have an answer really ultimately to this.
I see. So what makes quantum field theory successful in combining quantum physics and relativity?
Good question. With relativity, it's really the key was, and I think Newton was immediately aware of this, that he didn't have a mechanism for gravity. So if you ask how does the sun gravitationally affect the planets, then it really did look like a spooky action at a distance. So speaking of spooky action, Newtonian gravity is like that, and it sounds instantaneous. I believe Newton suspected that there was a finite speed of propagation. He certainly speculated on that, but there were no experiments at that time to show any of this. So in that sense, I think there was already a problem there. And then, of course, Maxwell was ultimately, the whole electrodynamics developed. And I think Maxwell, Faraday probably experimentally, and then Maxwell theoretically were credited for this invention of the concept of the field. And that's really what helps you, because with any interaction in physics, when you introduce a source of a field, if you introduce a charge or introduce a mass, if you like, for gravity, what physics then says is that you are initially only going to perturb the local space. And never faster than the speed of light. And then that local perturbation propagates further, a bit like waves in a pond. When you throw in a stone, you cause ripples and they propagate at a finite speed. So if you insert a mass somewhere, gravity ought to propagate exactly in the same way. And once you phrase it through a field, then relativity naturally is basically included in the field equations. So the key idea is not to let masses couple directly to one another without an intermediate thing. But as long as you introduce something continuous and this ripple propagates between the two, you're completely okay with relativity.
I see. So what do you think about Galileo and Newton, who is the greatest physicist of all time and the greatest philosopher of all time?
Oh, that's great. Okay, all of these questions. Probably, again, if you look at the jump made, I think when you evaluate these, either physicists or philosophers, I think you have to evaluate them as part of their own time. I think in physics it's usually between Newton and Einstein, and I think either one or the other. Certainly Galileo had many of these ideas even before Newton, and I think Newton inherited all of these things. But if you just look at how much Newton did with the understanding of mechanics, then gravity, then optics, then many other areas of physics, and then coupled to the fact that he had to come up with calculus, more or less, just to even describe motion. If you ask a mathematician, probably they would include Newton into top 5, even of their own mathematicians. So that's kind of why I would put Newton up there. Einstein certainly very close. Maybe that's your 1 and 2. if you like. And what's tremendous about Newton, and I think this is true for many people, is that he was very young when he did that, right? We are talking about between the age of 20 and 22 or 24, all of this came out, ridiculously productive, I think. With philosophy, maybe again, you have to look at it kind of within the context of these philosophers. I'm extremely fond of the ancient Greeks, no doubt about it. I think I can't find anyone in the kind of more modern context that's exciting as reading, for instance, Plato's dialogues, Socratic dialogues. So to me, that's still kind of, and if you look, sure, some of these things are, some of the discussions are maybe a little bit naive from our present context and so on. But if you look at the range of questions that they targeted, it's incredible. And like I said, many of these issues that they raised, and they even left them open, we don't know how to answer them. It's not that we've answered them after 2,500 years. So I think I would certainly put someone like Plato. Again, it doesn't mean, I would say in terms of the influences and in terms of the ideas, it doesn't necessarily mean, for instance, that I buy the idea that there is a Platonic world, that that mathematical objects exist independently in some kind of heaven of their own and so on. I don't know whether this is true. Probably not. But somehow I think if you just look at the sheer impact of all of these ideas, it would probably be Plato.
Right. Yeah. And what do you say when some people say that Einstein's genius is overrated? And perhaps on the other side, Nikola Tesla's contribution is underrated.
Great question as well.
What do you think of that?
Yes, I think it's very difficult to compare the two because I think you should compare Tesla with someone like Faraday. Because Tesla never really went into the formal mathematical side of things, which is why I wouldn't compare him maybe to a theoretician like Einstein or Maxwell or whoever. He certainly didn't have those abilities of those guys. But I would say, Faraday is someone that physicists would maybe consider the greatest experimental physicist of all times, and I think Tesla certainly compares to that. I mean, the ideas there, if you look at it, the impact on fundamental physics as well, which of course, like I said, in Faraday's case, Maxwell was there to actually do it formally. I think it's clear to me that partly the reason why Tesla, in a way, is underappreciated is because of this, because of maybe the lack of some kind of theoretical underpinning for many of these things. He also was probably a very quirky character, right? Which maybe didn't help these things. But I think in general, this discussion that you said, the genius, I really, clearly these people are very smart, able. Whether the word genius is the right, because it almost implies it's God-given, they were born like that. I think behind all of these people is an insane amount of investment into these problems. These are people who were capable of focusing on one and the same question for long periods of time. Newton would, for instance, the story is that he would even forget to eat.
Oh, really?
He would skip lunches, dinners. Then he would go to the kitchen, see an empty plate and say, "Oh, I must have eaten my dinner. I'm going to go back to the study." And I think true of Tesla as well. I think that he only slept 4 hours a day apparently and worked the rest. Wasn't married, ignored all the other kind of aspects of life. So I think if you look at it in that context, it's certainly something that's required. Whether that's inborn or not is a different question. Are all of us capable of focusing to that degree and over those long stretches of time? I don't know. But these guys certainly invested an insane amount of time.
So what is there left to explore in quantum physics to make it a complete finished theory? Is there something even beyond quantum physics?
Good point. Yeah, I think the main question for quantum physics is really to go into domains where we haven't tested it at all, and it really isn't tested in the macroscopic domain, and we don't know. There are so many theories about what could happen to quantum mechanics. Usually, I tend to call them hybrid theories.
Okay.
Because you kind of assume, when you study some of these things, you assume that part of your system is quantum, and you say, these are quantum bits, I tested them, I know exactly what I can do with them. And then you couple that to another system, X, which you now want to conclude something about. And it's a hybrid theory because initially you could even assume, let's say that system obeys another kind of theory. And we have all sorts of extensions of quantum mechanics, generalized probabilistic theories, for instance, all sorts of other ideas that come there. And then you can say, if the two couple to one another, what happens next? And I think we haven't tested this at all, neither with gravity, for instance, nor with living systems. And I think this is something we are hoping to do in the near future. Beyond that, again, this is only kind of more like hope and intuition, maybe, is that you really, it would be kind of funny if this was the final word, that somehow we really came across and that's the theory of everything. We have this standard model now, which is really at best a kind of phenomenological description. It's the description that maybe is the most compact one we've been able to come up with. But it still contains something like 26 free parameters, which you have to insert there to get all the masses and all the couplings and everything else. So, it doesn't look clean at all. It looks too arbitrary. So I'm almost certain that we will go beyond that and we will reduce even that to something simpler. But again, my guess is, here is where I disagree with people who talk about collapse of quantum mechanics. I don't think we're going to discover that quantum collapses and classical again takes over. I think it's going to be something even more super quantum. I don't know how to call it. And then we will realize that quantum mechanics is like a special case of that. That's kind of what knows. We have no indications at the moment. People are playing mathematically with these equations, trying to come up with something that looks consistent. But again, experimentally, we have really no reason to doubt it at the moment.
Relativity and quantum mechanics, two of the best ways to describe the universe.
They are the best because for some reason, and again, it would be nice if it wasn't like this, and maybe one day it won't be like that. They really cater to the two different parts of the universe in terms of size and complexity. So relativity really, or gravity at that level, is all about large macroscopic objects. And we really need it there. We know that the universe, as far as we test it, really does obey the laws of general relativity. I mean, there are some discrepancies there. It's not, I think that kind of understanding is not as firm as the microscopic one where quantum mechanics really rules. I'd say, we've had 120 years of absolutely no deviations from experiments, from the laws of quantum mechanics. And but it's funny that we are viewing the universe in this kind of almost dichotomic way, right? That the small objects, quantum mechanics, small and smaller and smaller, and then we don't know how far that goes. But then these large objects, starting with solar systems and then larger and larger objects, clearly the universe at that level is governed relativistically. And again, because these objects are really very complex, it's hard to imagine that quantum mechanics could play a fundamental role now at that level. In the early universe, possibly, people say, but when the universe was very small, then surely both gravity and quantum mechanics could have been critical. And I think that's what people are looking maybe for some signature. But at the moment, they look completely separate.
Yes. So why the phrase wave-particle duality is no longer so popular in quantum physics?
Good point as well. Wave-particle duality was probably historically important because I think people, the history of physics is we have Newtonian physics, it's all about particles. And we have optics, which was really all about waves. Newton, incidentally, thought of optics in terms of particles as well. Because I think he was observing that under some circumstances, a beam of light would also travel in a straight line. He knew that ultimately there would be diffraction, interference, and he was struggling how to understand that. But it looked to him very suggestive that much as particles travel in a straight line when you don't have a force on them, he thought, look, light also, a beam of light, like when you have a laser pointer, also travels in a straight line. And so it's not a crazy idea that it's made up of particles. And of course, quantum mechanically, it is made up of particles, funnily enough. But he found it difficult to explain all sorts of other things. And at that point, somehow it seems that physics had to talk about two kinds of fundamental objects, material objects and then waves. And quantum mechanics unified these two. That was the great thing about quantum mechanics. But I think in the early days, there was a lot of confusion. Because when de Broglie came up with this idea that matter can also behave like a wave, that was really mind-blowing. That was completely revolutionary. And people started doing experiments, diffracting electrons, and they realized, okay, it is like that. And then I think people were starting to say, well, wait a second. I mean, when should I say that it behaves like a particle, and when should I say that it behaves like a wave, right? And there were even jokes from some leading physicists saying maybe Mondays, Wednesdays, and Fridays it's a particle, right? And Tuesdays, Thursdays, and Saturdays. So it's kind of, but now we don't need to do that because this is kind of an old-fashioned discussion, if you like, in the early days when they were really trying to come to terms with what it means to unify waves and particles. I think now the formalism already as we know it unifies these things. So, when you write an equation for a particle, Schrödinger came up with the first kind of meaningful equation of that kind. He wrote it down more or less as a wave equation. So already acknowledging fully that there is a kind of wave that's associated with this particle. Now, of course, undeniably, these waves do behave as though they are made up of particles under some circumstances. And again, this parallel with Newtonian thinking is very interesting because Newton could also say, well, I know that there are diffraction and interferences and all of that, but look, under some circumstances, light does behave like a stream of particles. And I think that's the idea. If you set up your experiment in the right way, you can get a very kind of particle-like behavior. Whereas in the other extreme of that, you will get a wave-like behavior. You will get all the interferences and everything. But I think quantum mechanics covers it all, both of these and everything in between. So in that sense, I don't think you have to keep asking, is it a particle or is it a wave? Because we have an answer to that, if you see what I mean.
Okay, so why fuzzy logic is more appropriate for quantum physics than Boolean logic?
That's also good. That I think was, and actually still is in many ways. It's a very interesting way to think about what is it that really new physics tells us about the world. And that's always with the physical theory. That's why I firmly believe that philosophers, but maybe natural philosophers, maybe even moral philosophers one day, but we're not there yet, I think. But natural philosophers should certainly be aware of what's going on in science, and in particular in physics, because that gives you maybe the most fundamental description of the universe. With relativity, you could think, for instance, that the geometry of the universe is not Euclidean. It's not flat as we thought before that, but actually there's a certain curvature to space and time, which Einstein, kind of brought into the game. With quantum mechanics, if you ask me, wait a second, what is it that does quantum mechanics also modify geometry? I don't think so. I don't think that's the right way to go. But it's maybe more what you mentioned, because in classical physics, things really either are or they're not, or they're either in one place or they're not in that place, they're somewhere else. So it really is a binary. It's completely Boolean logic. With quantum mechanics, you get this and that's kind of, as we said, the crux of quantum mechanics. You get these superpositions, entangled states, and all of that. And it looks like you have all of these classical possibilities at the same time. And then the question is, what kind of state in terms of logic does that correspond? You know, if the particle here is your logical 0 and a particle here is logical 1, what does it mean to be 0 and 1 at the same time? And already our grammar is wrong there, because when I say 0 and 1, I really have to specify what that and means. There's a particular meaning in quantum mechanics, and we know what kind of experimental consequences it has. But it's not our normal and that we use in our language, or maybe Boolean and. It's just not like that. It's not or either. It's very weird. So if you say to me, so is it here or here? No, it's not like that. It really is somehow in both. Right. But if you say and if you then say, but wait a second, if I detect it, I'm only going to get a click here or here, then why are you telling me that it's here and here at the same time? You get into that kind of trouble. And some people, I think, most notably, possibly von Neumann, thought that what this means is that the logic we should be using shouldn't be Boolean. It should have more alternatives, non-binary logic. Now, how many alternatives in between is very questionable at the moment. Some people use the three-valued logic, so the superposition would be your third value. But the problem with that is that we know that there are infinitely many possible superpositions, depending on how much of it is here and how much of it is there. It's a real number, right? Between 0 and 1. And then some people say, that means maybe I need infinitely many logical values between. And that's what people are playing with.
Right. So how can quantum physics be relevant for macroscopic objects?
How can it be? I think maybe one way to say it, there is this discussion usually takes place when I go to some of these meetings on quantum biology, because people say, what do you mean by quantum in the biological system? It's a very difficult question. Because why is it difficult? Because let's put it very, very kind of superficially. There is a trivial way in which something is quantum, and we are looking for something beyond that. But it's not easy to characterize. It's I can explain it a bit better. A trivial way is simply the fact that quantum mechanics explains the atomic structure, explains how atoms bind together to form molecules. Stability of matter is all about quantum mechanics. Pauli exclusion principle, uncertainty, all of that. So if we didn't have quantum mechanics, atoms wouldn't be here. We wouldn't be here to talk about it. Nothing would be here. So trivially speaking, obviously biology somehow capitalizes on the fact that there is stability out there. But I would call that more trivial because, you know, that forms the structure there, and it's just a given to us. It's already there. What would be non-trivial is if, for instance, biological systems, that to me sounds fascinating, if biological systems have evolved, if they've learned how to maintain a large superposition for long enough that it could do something useful biologically, that to me would be non-trivial. Why? Because if you tell a physicist, for instance, take a biological cell, do you think it could exist in a superposition of two spatial locations? Most physicists would say, no, it's too large. It's just going to decohere so quickly. You're going to get signals, whether it's here or here, so rapidly that you will never keep this in a superposition. And that's what I'm now asking. Could it be that some superpositions of the, maybe not the whole cell, but maybe bits of the cell, maybe for short enough time, are really in a superposition? And does this really matter to biology? I think this would be amazing. And it would be surprising if evolution found all sorts of mechanisms and gadgets along the way. It would be surprising if some mini quantum computations were not taking place there. So that's kind of what we mean by when we go into the macroscopic domain. Obviously, many things in the domain are already quantum. Right. Like I said, large material objects are like that because quantum mechanics is the way it is. But I think what we are looking for quantumly is, can we go beyond? Is there something that would really surprise us? That's the idea. Right. So how important is geometry for the general theory of relativity and quantum physics? In two very different ways, and that maybe also how you could understand why the two theories are difficult to put together. That's kind of one. You could almost crudely say that quantum is all about algebra.
Yeah.
I think I will correct myself in a second about it. It's kind of almost all about algebra. General relativity is all about geometry. It really is all about curving space, and even thinking of gravity as curved space. So, we're thinking of a planet as being attracted to the sun, not by some mysterious kind of Newtonian force, but we are simply thinking that the space-time has a very weird curved shape in between, and that's exactly, it's almost like the planet is falling towards the sun, and the sun is sitting here at the minimum. So that's kind of how, in a way, general relativity, almost eliminates gravity and says it's all about geometry. It's really everything can be accounted for if you allow curvature of geometry. Quantum physics, on the other hand, you never need to think about it like that, other than the following point. It's a very different kind of geometry, and it's to do with vectors. It's to do with vector spaces. And it's nothing to do with gravity. It's a different thing that poses us into that. It's in fact the superposition principle. So when you think about how we describe things in quantum mechanics, is that you assign a state to a quantum system. You say, what is the current state of this system? It describes all the properties that are relevant for quantum mechanics. Now, what quantum mechanics says is if you have two such states, for instance, particles sitting here and particles sitting here, quantum mechanics says again that the sum of these two states is yet another allowed state. That's your superposition principle. And if you think what in mathematics has this property, it's vectors. If I have one vector, another vector, the sum of the two vectors is yet another vector. And you say, great. So these spaces have this fancy name, Hilbert spaces, because of the mathematician David Hilbert. But in fact, they are like that because of this superposition principle. It's the best way in which we know how to capture the superposition principle. So geometry plays kind of a role in both, but very different kind of geometry, and for very different reasons. And the question is, could they somehow be merged together? Could they actually be related to one another? And there are some very creative ideas in that direction. There are people, for instance, who would say that when you talk about superpositions, you could think of that as a curvature. You could say the classical world, you could think of as the flat Euclidean manifold, which means an object is here or there, but not in two places at the same time. And any quantum effect on top of it, you can think of maybe as some curvature. And people have explored this. It's called geometrization of quantum mechanics. Can we make it geometrical in the same way as general relativity? I think very exciting ideas. Again, like I said, none of them are at the level where we could really test this properly. So we don't really know if any of these ideas make sense. But there is a lot of exciting work.
How can you compare linearity of quantum physics with nonlinear modifications of quantum physics?
Yes, that actually goes in it's related to the previous question, in the sense that if you were to introduce nonlinearity, you would then challenge this statement that any sum of two physical states is yet another state. That's exactly what it means to be nonlinear. That nature favors certain states over their combinations, over their superpositions. And in fact, people who believe that quantum mechanics would collapse introduce this nonlinearity as the mechanism for the collapse. So they say, yeah, maybe you can make a superposition, maybe it could last for a certain period of time, but sooner or later, something, and this would be this nonlinearity. Of course, you have to explain why there is a nonlinearity. What's the cause? That's a different discussion. But a nonlinearity is usually there to select one of the two options. And so it's a very different theory, because the theory would say, there is a limitation to the superposition. It's not as universal as quantum mechanics. You can't superpose anything you want. That's kind of what this would do.
Right. How do you perceive consciousness in the universe? Is there a connection between quantum physics and consciousness? And do you believe an AI can become conscious?
It's also a very good point, because I think about it frequently in the context of quantum observations, right? Measurements, as we said. How do we perceive reality? And I think it would be nice to, at least computationally, maybe within a quantum computer, come up with something that resembles human perception.
Right.
Or any biological, for that matter. Even lower species clearly are more capable of perceiving and manipulating things than even our best computers. So I think that this research will develop, and I think ultimately my guess would be that we could engineer artificially intelligence, or whatever you call it, consciousness, whatever property you think we have at some level. I believe that computers will be able to do that. Now, I'm against. I believe that simply because it's a very trivial argument, in the sense that I think we are simply governed by the laws of physics. There could be some new laws of physics that we haven't discovered, but nevertheless, there will be some interactions between the constituents that make us up, our brains, whatever leads to consciousness. And I think it's some kind of computation, according to this logic. So whatever computer obeys the same rules that we think are obeyed in our head will ultimately have to be able to mimic this kind of stuff. Of course, providing we understand what it is that we need to do. It could be a very complicated problem. So I'm more on that side of things. I'm not. I know that some of my colleagues, although not in physics probably, this is more in neurosciences, maybe philosophy, they go in the other extreme, where they say, oh, they're called panpsychists. They would say, oh, everything is conscious. Every bit of the universe is kind of conscious. So somehow, they're trying to bridge this gap between conscious and non-conscious entities in a way to say, but consciousness is already built into the whole universe. And I think they're wrong. I think it seems to me to be an emergent property. It's clearly a question of certain complexity. But I also think we don't know enough at that level to know exactly what we need to reproduce.
I see.
But I think one day when we understand it, I don't see why we couldn't reverse engineer it. It sounds natural to be able to do that.
Right. So how do you replace matter and energy by the concept of quantum information?
Yes, this I thought was a fantastic way of. I thought that ultimately was actually the greatest contribution of the field of quantum information to physics. That it really teaches us somehow that all of these physical systems resemble one another. You can distill this information content and only talk about these quantum bits. And you don't need to worry what is it that they represent. Any bit of matter or energy could actually be made out of quantum bits. And this is a beautiful unification of quantum mechanics. And in fact, why I consider it a good way of thinking about physics is that when you're describing interactions between different systems, what really determines how they interact is what kind of information processing capacity they have. So one way of understanding, for instance, why when you couple a quantum system to a classical system, why this leads to a collapse, is simply because a quantum system has a much bigger information processing capacity than the classical. So it's a bit like having a very wide channel. We can communicate a lot of information, then suddenly narrowing it down into a much smaller channel. That would be your classical system. So there is simply nowhere for this extra information to go than squeeze into this binary 0 or 1. That's the only thing you can get out of it. So to me, that sounds like a very good metaphor. And also, And also, it's, I think, a good guide for the next theory, because now you can also say, oh, okay, that sounds nice, but what if you have a theory that's even more powerful than quantum mechanics? That would be interesting, because now you'd be fitting something with less the capacity for information processing into a big one. What does that mean? What kind of consequences does that have? So to me, it seems that consistency in physics definitely at some level requires us to couple systems of the same kind of information capacity. And that to me sounds like a good way of talking about even axioms of quantum mechanics.
Right. So why the second law of thermodynamics is problematic for physicists?
Second law is very problematic because there is one way of putting it. Let's put it in this way. We have these two laws of thermodynamics. The first one is energy conservation, and the second one is this second law, which says that the disorder in the universe always increases. In a closed system, you can never decrease disorder, and that's usually linked to the arrow of time, right? That things always happen in the macroscopic world, always happen one way, but never in the reversed fashion. And that's a mystery to a physicist, because all of our fundamental laws are reversible. There's no arrow of time anywhere in our equations, in Newton's, in quantum, anywhere you look, it can go one way, but equally valid in the opposite direction. And so for us, the question is really how to understand this second law. And it seems different to the first law, because the first law is exact. The first law says energy is always absolutely conserved. There's no violation of that. It's not statistical. It's not that half of the times it will be conserved, or half of the times they get more energy, the other half less. On average, it's okay. No, this one says whatever process you have in nature, energy is absolutely conserved. Looks very nice and clean, very prohibitive. And now comes the second law, where you say, well, at the fundamental level, things can go back and forth, but somehow if you add some statistics and complexity, they no longer will go backwards. So it doesn't look as clean as that, if you like. And to me, it seems that it's statistical in nature. It only really emerges under some circumstances. But it seems to me at the really fundamental level, if you could control everything perfectly, it seems to me entropy would always be zero, in the sense that you would never increase or decrease entropy. You could always go in one direction and go backwards.
I see. So what do we know about black holes today?
Black holes, again, we did a very good point, linking it now to the previous question, because, and that's yet another way of thinking about why general relativity may not be compatible with quantum mechanics. And I think Stephen Hawking was very fond of emphasizing this aspect, and Roger Penrose is another famous physicist in that direction. So basically, GR, in general relativity, you have these objects which do contain this irreversible behavior. And that's because the theory says that if you have something massive enough squeezed into a small enough volume, it will be so gravitationally attractive that nothing could actually escape that object, right? That's that famous event horizon, which would be the boundary of that object, beyond which even if light goes into it, you will never be able to get any signals outside of it. So that sounds like a good prediction of general relativity. There is some experimental evidence for black holes of a very different nature. I think usually you're talking about gravitational lensing and indirectly they exist. Of course, no one has really tried to throw something into it and extract it. But it seems GR suggests that this is a one-way street. There's no returning there. Quantum mechanics, like I said, is governed by completely reversible transformations. And now you could say, well, if I want to explain black holes quantum mechanically, how do I do that, given that you're telling me that in general relativity, it only goes in one direction, but actually quantum mechanics says, no, whatever you do in one direction, you should be able to undo that transformation. And I think that's a big debate in the community. Black holes are very strong gravitating objects, and I think it's very difficult to see that we will be able to experiment quantum mechanically with anything like that. I'm more hopeful when I say kind of quantum gravity. I have in mind the other extreme, where the gravity is very weak, almost Newtonian, and then you ask, what happens now when I superpose masses and test gravitational fields? So this is in the low energy regime. And I think our first bits of evidence that gravity is quantum will come from there. That will be kind of my bet. Black holes are the exact opposite extreme. You have to take the next order of approximation, you almost have to go to all orders of approximation in order to do that. And then no one really knows. There are two camps, and they're really betting on opposite outcomes. I think there are people betting that irreversibility will prevail, and that means you really would have to modify quantum mechanics. And that leads to what we already discussed, all sorts of nonlinear formulations of quantum equations. On the other hand, there is also a very strong activity in this research direction of trying to quantize this and say, well, information, a bit like with the second law, it's only apparently lost. But if you wait for long enough, black holes will ultimately evaporate, and you will be able to extract exactly what you put in. You'd be able, if you had enough experimental precision, you'd be able to tell exactly what it is that fell into the black hole to make it up. And I mean, of course, you can see that this question is extremely common. I had no idea how one would even test it. But I think it's nice, at least theoretically, to know that it's possible that black holes too are quantum mechanical. But then I would say this idea of event horizons and irreversibility would be more statistical. It would be more like the second law that we were discussing rather than a fundamental law in the universe.
Professor Vedral, thank you so much for this conversation. And I would just like to mention that you wrote several books on physics, which are fantastic, and I encourage people to check them on your website, vlatkovedral.com.
Thank you.
Thank you so much.
Thanks very much. Pleasure. Thank you.